Okay, so we're going to move into random variables. And what we're going to be going into is making distributions. And what these are going to be called is probability distributions. So before we do that, we just need a little bit about what random variables are. And it's not really that complicated of an idea. We've already been using random variables all along. So if we roll a fair side die, the possible outcomes that we can get are 1, 2, 3, 4, and 5, or 6. Each of these numbers has a probability of 1 in 6. So rolling a die is a probability experiment whose outcomes are numbers. The outcome of such an experiment is called a random variable. So these are my random variables. I can get a 1, 2, 3, 4, 5, or 6. So a random variable is a numerical outcome of a probability experiment. So we're only using this for numerical things again. So remember discrete and continuous. A discrete random variable are random numbers whose possible values can be listed. And examples include rolling a number that comes up on a die. So those are continuous because those can be listed. I can list 1, 2, 3, 4, 5, and 6. Number of siblings a random chosen person has. They can go, okay, I have either 0 siblings, 1 sibling, 2 sibling, 3 sibling, 4 siblings, 5 siblings, but that's something I can list. So these were your things that were whole numbers, essentially. Like I said, it's an oversimplification, but think of it that way. Continuous random variables are random variables that can take on values in an interval. So example for a height of a randomly chosen college student, they could be 5'6", or they could be 5'6.5". They could be 5'6.75". They could be 5'6" and 5/8. There's a range of values in there. The amount of electricity used to light a randomly chosen classroom. So you randomly choose a classroom. It might require, like 60 watts to light that room, but it may require like 60.2 in another classroom. So this was the case when it was continuous. This is when we were dealing with decimals. All right, we can have somebody who is like, 72.3 inches tall. So we can have that, or we can use 60.8 watts. So a probability distribution for a discrete random variable specifies the probability of each possible value of the random variable. So going back, some of the things we know is that if I'm looking at any kind of variable, what we're going to see is the probability that it occurs is always going to be between 0 and 1. And if I do a summation of all my probabilities, that summation should equal 1 because it covers all my events. So we're talking about the dice roll. I have 6 outcomes. Each one has a 1 in 6 chance of happening. If I add that up, that's going to give me 100%. So a fair coin, meaning that when I toss the coin, it's equal heads, equal tails. That's a fair coin, so it's not weighted. A fair coin is tossed twice. We're going to let X be the number of heads that come up, and we want to find the probability distribution of X. So we know these are the things that can happen. So what I have here is my sample space. That's all this is, sample space. That's all my outcomes. So I can get 2 heads, a head and a tail and a head, or a tail and a tail. So the number of heads I have here are 0 if I get 2 tails, 1 if I get just a tail and a head, 1 again if I get a head and a tail, and if I get 2 heads, the number is 2. So these are my random variables. So the possible values that my experiment can take is I get 0 heads, 1 head, or 2 heads. So what we're going to have here is we want to mark off, like I said, this is number of heads. That's my discrete random variable. And it's going to be discrete because my choices are, like I said, whole numbers. And this is going to be the probability of each variable. There you go. Probability of each variable. So if I get 0 heads, that happened 1 out of 4 times. So that is 0.25. If I get 1 head, that happens 2 out of 4 times, or 50%, or 0.15. If I get 2 heads, once again, that one happens 1 out of the 4 outcomes that I have, that is going to be 0.25. So what we have down here at the bottom is this is what we call a probability distribution. So all a probability distribution is it's going to be a list of my random variable and the probability that each variable happens. So this is not really any different from any distribution we did before. So you think of it as being more like your relative frequency distributions. You're not going to get whole numbers. You're going to get probabilities. So you're going to get values between 0 and 1. So we're going to decide whether each of the following represents a probability distribution. So first thing to remember is that my probabilities are always going to be values between 0 and 1. So automatically, this doesn't work because that is not between 0 and 1. The other thing that we know is that the summation of all my probabilities is supposed to equal 1 because it represents 100% of my situations. So if I add up what I have here, let's see, 5, 6, 7, 8. I just lost count just a second. 10, 13. So that's 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That sums up to 1. So here, the summation of my probabilities is 1. So this one is okay so far. This last one here, if I do the summation, I think we already see, we said 2 problems here. If I look at that, that is a probability, once again, that is not between 0 and 1. So that is one problem. Also, if we sum this up, we would get 3, 4, 5, 6, 9, 10, 11, 12, 13, 14, 15, 16. We get a summation of my probabilities of 2.66. So it's not even 1. So that one is also one that we have to cross out. So only thing here that actually represents a probability distribution is the one in the middle, because all my probabilities are between 0 and 1, and the summation of my probabilities equals 1. Okay, so we want to make a probability distribution of the sum of 2 dice. So we look at this, we take 2 dice and we roll them and we sum their numbers. My random variables, and they're going to be discrete random variables again, we could have 2 as an option. They could sum to 3. The summation could be 4. The summation could be 5. The summation could add up to 6, or it can add up to 7, or it can add up to 8, or it can sum to 9, or it can sum to 10, or 11, or 12, which makes sense because if I take the sum of 2 die, at least they're going to both roll a 1 and we get a 2. At the most, they both roll 6, we get a 12. So we cover everything in between 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So remember that if we want to figure out what are my total outcomes, we could count everything, or we can use those counting principles. I have 6 choices for my first die, 6 choices for my other, so that is 36. So the probability of each event is going to be out of 36. So 2 is 1 out of 36. Which is approximately 0.028. If we look at 3 now, we have 2. 2 times can we get a 3? We can roll a 2 and then a 1, or we can roll a 1 and a 2, or a 2 and a 1. That's 2 different ways that can happen. Another option for me is my 4. So my 4 can happen 3 different ways. So that is 3 out of 36, which is approximately 0.83. Oh, sorry, 0.083. My other option is I could have the 5s. There's 4 5s out of 36, which is approximately 0.11. We see there's 1, 2, 3, 4, 5, 6 out of 36. So that will be approximately 0.14. Second, I'm seeing what I'm rounding to. 39. There we go. Round everything to the same place. 7s, I have 6 7s. The rest of this will start repeating. And then we start going back down. So we have 5 8s, we have 4 9s, we have 3 10s, we have 2 11s, and we have 1 12. So these just happen to work out very symmetrically, but this isn't going to be the case all the time. And it's partly just because of we're doing essentially we're going to be like binomial probabilities right now. And this happens a lot when we do that. Essentially we're doing binomial probabilities, and the probabilities of independent events alone are always the same. So that's why we're getting these symmetric distributions. But we see that if we're going to do, a graph of this, it's pretty symmetric. It's exactly symmetric. Okay, so 4 patients have made appointments to have their blood pressure checked at a clinic. We're going to let X be the number of them that have high blood pressure, and the probability of X is as follows. So we have the probability that 0 of my 4 patients have no high blood pressure. That's about 23% chance. The probability that 1 of my 4 patients has high blood pressure is 41. The probability that 2 of my 4 patients have high blood pressure is 27%. The probability that 3 of my patients have high blood pressure is 8%. And the probability that 4 of my patients have high blood pressure is going to be 1%. So I want to find the probability that 2 or 3 of my patients have high blood pressure. So that is going to be the probability that 2 have high blood pressure and the probability that 3 have high blood pressure, because that's an OR event. And we're not really worrying about an overlap here. So the probability that 2 have high blood pressure is 0.27. The probability that 3 have high blood pressure is 0.08. So there's a 35% chance that if I randomly select some, or on a random day, if my 4 patients come in, that I expect that 2 or 3 of them have high blood pressure. What's the probability that more than 1 has high blood pressure? So more than 1 would be this area. So more than one is the probability that 2 or 3 or 4 have high blood pressure. So that's 0.27 plus 0.08 plus 0.01. So in this case, we are going to have 0.36. So there's 36% chance that more than one of my patients is going to have high blood pressure. And the last one is at least one. So at least one means that at the low end, I expect one of them to have high blood pressure. So this is going to be my at least one. So in that case, that is somebody that's going to have, I'm going to have 1 or 2 or 3 or 4 of my patients is going to have high blood pressure. So that is going to be 0.41 plus 0.27 plus 0.08 plus 0.01. If we add that together, we are going to get 0.77. Or we could have done this. 1 minus the probability that 0, because that's the only one that wasn't included, at least one, that none of them have high blood pressure. So we could have done that instead. Oops. The following is a probability distribution of the random variable that represents the number of extracurricular activities a college freshman participates in. So part of this is just to kind of get some terminology out there, or kind of the wording and understand it. We want to find the probability that a student participates in at least 2 activities. So when I say at least 2 activities, that means at the lowest is 2 activities. So this is either in 2 or 3 or 4 activities. So that's 0.45 plus 0.21 plus 0.14. So that is going to be 5, 6, 7, 8, 9, 10, 4, 5, 6, 7, 8. So there's an 80% chance that a randomly selected college student would participate in 2, 3, or 4 activities, or at least 2 activities. We want to find the probability the student participates in more than 2 activities. This is more than 2. So that is they participate in 3 or 4 activities. So that's 0.21 plus 0.14. So that is going to be 0.35. So there's 35% chance they participate in 3 or 4 activities, or more than 2. And then the last one, what is the probability the student participates in at most 2 activities? So at most means that is the maximum that they can do. So that is the probability they participate in 0 or 1 or 2 activities, because at most they're doing 2. So 0.06 plus 0.14 plus 0.45. So we will have, I believe that's 60. 4, 5, 6, yes. So there's a 60% chance that a student is going to participate in at most 2 activities. It's 65. There we go. Let's say I just noticed I was comparing to its these ones. I just see a notice here. These 2 are complements of each other, because this accounts for 3 and 4, but this counts for 0, 1, 2. So that was just a way I checked that, saw another mistake there. Yeah. So just like I said, just be careful with the wording because sometimes it's telling you whether what you're including. So if I say at least 2 activities, that means the lowest I can have is 2. If I say at most 2 activities, that means the most I can have is 2. If I say more than 2, then 2 is not going to be included.